Now that we've talked about multiplying a matrix by a scalar, we want to talk about how to multiply two matrices by each other. You would think, based on what we've seen with matrix addition and subtraction, that when we multiply matrices, it would just be about multiplying corresponding entries. But in fact, that's not how we multiply matrices. So let's look at an example here. Let's say we maybe have the matrix 2, 3, -1, 0. And we want to multiply it by another matrix. We'll say 0, 1, 0, -1. The way that we're going to do that is using dot products. In other words, unlike addition and subtraction, we don't just take 2 times 0 is equal to 0, 3 times 1 is equal to 3, -1 times 0 is 0, and 0 times -1 is 0. We don't multiply corresponding entries. Instead, we use the dot product. So here's what the result is going to look like for this matrix multiplication. We're going to start by taking the first row of the first matrix multiplied by the first column of the second matrix. So we have the ordered pair 2, 3 multiplied by the ordered pair 0, 0. In order to multiply those ordered pairs by each other, we multiply the first entries 2 and 0, and then we add to that the product of the second entries 3 and 0. So we're going to get 2 times 0, the first entry in the first row and the first entry in the first column, plus 3 times 0, the second entry in the first row and the second entry in the first column. And the result there will, of course, be 0 plus 0, or 0. That entry is going to go here in the 1, 1 position. Then we again take the first row, 2, 3, but this time we multiply it by the second column, 1, -1. So we say 2 times 1 plus 3 times -1 is equal to 2 plus a -3, or 2 minus 3, that's a -1. That's going to go in the 1, 2 position. Then we take, now that we've done the first row across both columns, we move to the second row of the first matrix. So we take the second row multiplied by the first column, so -1 times 0 plus 0 times 0, and the result there is 0, and that entry goes in the 2, 1 position. And then finally, we take the second row by the second column, and we get -1 times 1 plus 0 times -1, and we get -1, and that goes in the 2, 2 position. So each of these left-hand sides here of these equations are the dot products of those ordered pairs, where we multiply the first entries and then add to that the product of the second entries. And if these were 3 by 3 matrices, we would do the same thing. We would just have an extra entry where we multiply the third entry in the first row by the third entry in the first column, and we add that on to the expression here on the left. So we can take as large of a dot product as we need to. Now, the thing to remember about matrix multiplication is that not every matrix can be multiplied by every other matrix. Remember that with matrix addition and subtraction, the matrices had to have exactly the same dimensions in order for the sum or the difference to be defined. Well, with matrix multiplication, the dimensions don't have to be exactly the same, but we have to have the same number of columns in the first matrix as we have rows in the second matrix. So here's how we want to think about that. If we're multiplying two matrices and the dimensions of the first matrix are rows by columns, remember we always write dimensions as rows times columns, and then we're going to multiply that by the second matrix, which is also defined as rows times columns in terms of its dimensions. The way to know whether the matrix multiplication is defined is to look at these two middle numbers here, the columns in the first matrix and the rows in the second matrix. These two values have to be equal to each other in order for the product to be defined. So for instance, with this multiplication we just did, we multiplied a 2 by 2 by a 2 by 2. And so when we look at those middle numbers, we have 2 columns in the first matrix and 2 rows in the second matrix. That's the only reason that the matrix product was defined at all. In other words, if we were trying to multiply a 2 by 4 matrix by a 3 by 2 matrix, we couldn't do it because the 4 and the 3 are not equal to one another. We don't have the same number of columns in the first matrix as we have rows in the second matrix. And that leads us to another interesting point, which is you might think, well, why can't I just flip the product around? Why can't I multiply the 3 by 2 matrix by the 2 by 4 matrix and change it like this? Multiply the 3 by 2 by the 2 by 4 instead, 2 by 4, and now it looks like my matrix multiplication is defined because I have these numbers equal to each other. But we can't do that because matrix multiplication is not commutative. So matrix multiplication is not commutative, which means that we cannot commute, we cannot move the matrices. So if I want to multiply matrix A by matrix B, that is not the same thing as multiplying matrix B by matrix A. I cannot change the order of the matrix product. I have to multiply matrix A by B. If I want to get a consistent result, I can't switch them around and multiply B by A. And that's why we can't just move these two here to get the dimensions to match. So that's the first thing we always want to check is the product of the matrices even defined by comparing the columns in the first matrix to the rows in the second matrix. And then if it does match, at that point we want to look at the rows in the first matrix and the columns in the second matrix. So the rows here and the columns here, because the dimensions of the product will always be the rows from the first matrix by the columns here from the second matrix. So once we know that the matrix multiplication is defined by these middle numbers, we can get the dimensions of the result from these outside numbers. And so you can see that with the 2 by 2 matrix multiplication, it makes sense that the result was 2 by 2 because we see these outer numbers here, 2 by 2. So as an example, let's say that we have a 4 by 2 matrix and we want to multiply that by a 2 by 3 matrix. If we look at the middle numbers, we can see that the matrix multiplication is defined because those numbers match. So then when we're talking about the result, when we multiply these two matrices together, what will be the dimensions of the result that we get, of the product that we find? Well, it's going to be a 4 by 3. So we know right away without doing the multiplication that the result will be a 4 by 3 matrix. So that's how we handle dimensions for matrix multiplication. The only other thing we want to make sure we know is that while matrix multiplication is not commutative, it is associative and it's also distributive. So matrix multiplication is associative and it is distributive. And so the associative property tells us that if we're multiplying three matrices together, we multiply A by B by C, A by B by C, we can first multiply A by B and then take that result and multiply it by C, or we could multiply B by C and then multiply A by that result and we'll get two equal values. And the reason is because essentially we're still always multiplying A by B by C. The order doesn't change, unlike commutative property. We're keeping the order the same, so we can associate the matrices in a different way if we want to. That property holds for matrix multiplication. And so does distributive property. So if I have the matrices A plus B, and then I want to multiply that by the matrix C, that's the same as multiplying A, C, and then adding B, C. Remember here too that order matters. So if I instead wanted to multiply C by, let's say, A minus B, that would be CA minus CB. So I have to apply the matrix C to A and B in the correct order. Here, because the C comes after, the distributive property tells us that that's equal to A times C plus B times C, where we multiply the C across these two. And here, because the C comes before, that means I'm multiplying C by A and then by B and taking the difference. So here I have C after A and B. Here I have C before A and B. But either way, that distributive property holds for matrix multiplication. And then the last thing that we want to know is that if we multiply a matrix by the zero matrix, we're going to end up always with the zero matrix. And it doesn't matter whether the zero matrix comes before the other matrix or after the other matrix. The only thing is that, of course, the zero matrix has to have the correct dimensions in order for the product to be defined. But regardless, as long as the dimensions are correct, if you multiply a zero matrix by another non-zero matrix, you're always still going to end up with the zero matrix. So let's just quickly do one more example so that we can see how this dot product works. Let's say we have 2, 1, 1, 0, 0, and 4. And we can see here that this is a 3 by 2 matrix. So let's go ahead and multiply this by a 2 by 2 matrix. So we'll say 1, 0, -1, and 3. And this is a 2 by 2. So when we look at the dimensions, we know that the matrix product is defined because the columns from the first matrix match the rows from the second matrix. And then we know that the dimensions of the product are going to be 3 by 2. So if we outline that here, we'll write it down here as a 3 by 2. This looks like it'll give us room for a 3 by 2. To find the first entry, we'll take the dot product of 2, 0 and 1, -1. So 2 times 1 is 2, plus 0 times -1 is 0. So 2 plus 0 gives us 2. So we have a 2 there. And then we take 2, 0 multiplied by 0, 3. So 2 times 0 is 0. 0 plus 0 times 3, or 0 plus 0, gives us 0. Then we go to the second row of the first matrix and multiply it by the first column. So we have 1, 0 times 1, -1. 1 times 1 is 1, and 0 times -1 is 0. So 1 plus 0 gives us 1. And then the second row, 1, 0, times the second column, 0, 3. So 1 times 0 is 0, and 0 plus 3 is 0, so 0 plus 0, or 0. And then the third row times the first column, 1 times 1 is 1, and 4 times -1 is -4. 1 and -4 is a -3. And then the third row times the second column, 1, 4 times 0, 3. 1 times 0 is 0, and 4 times 3 is 12. 0 plus 12 is 12. And so this is the product of these two matrices.